In this video, we're going to be talking about multiplying a vector by a scalar, as well as unit vectors. So if you've ever seen this notation around, and you've wondered what these I hat and j hat things are, those are unit vectors, and we'll be explaining those in this video. And to understand unit vectors, we have to talk through multiplying a vector by a scalar first, so that's what we'll start out with. And before watching this video, you want to make sure that you're okay with vector basics, the magnitude and direction of a vector. The magnitude is the how much. It's the length of a vector. It's always positive. And this is the symbol for it. The direction of a vector is just given by some angle. In this case, the direction might be 38.66 degrees. From our last video, we learned how to add vectors together. So you want to know that the resultant is just another word that means the sum. There are two ways of adding vectors, the parallelogram and component methods, and you'll definitely want to know what components are. We'll really be tying in this components definition in this video because it goes hand in hand with unit vectors. So let's say I had a vector A here, and I wanted to take some scalar, some number, say 2, and multiply it through our vector A. So what you do here is you take that scalar, that 2, and you multiply it into all aspects of the vector. So we do 2 times the magnitude, the length of A, 5, to get the magnitude, the length of B, 10, 2 times the x component, 4, to get 8, and 2 times the y component, 3, to get the new y component, 6. So if I took a scalar 2, multiply it by a vector A to get some new vector B, this right here would be a vector B. So the way you do a scalar multiplying into a vector is you take that scalar and multiply it through all sort of aspects of the vector, the magnitude and all of the components, except for the angle. This 36 degrees is the same. So multiplying a scalar into a vector has the effect of just increasing its length or decreasing its length. You can imagine what would happen if I didn't make this 2, but maybe what if I made it a half? Same thing applies. If it was a half, my vector B would be of length 2.5 instead, and its x component would be 2, and its y component would be 1.5. Now I can also multiply my vector A by a negative number, a negative scalar. Well, this is a tad bit tricky. I'm going to do negative 1/2 times our 4. That's going to get a negative 2. Now here's the thing. This is going to be a 2 in the negative x direction. Now negative 1/2 times the 3, that's a negative 1.5 in the y direction. And negative 1/2 times our 5, well, that's negative 2.5, but since the length, the magnitude of any vector is just a number with no sign on it really, I just write 2.5 here. But a way you can think about it is that this negative 1/2 multiplied by that 5 to make a negative 2.5, and in a sense, that negative sort of flipped the direction of our vector. Our new vector B now is pointing in the complete opposite direction as the original vector A. So just be careful to not put a negative 2.5 here, because the magnitude of any vector must just be a number, a positive number. Okay, so now we're really ready to tackle what a unit vector is. So take my vector A here. Remember this Cartesian vector form right here? And I told you guys to basically think of this as just meaning the x-coordinate of our vector A, and this meaning our y-coordinate of our vector A. Well, we are ready now to dive into what these two things are and why there's a plus here. I mean, why didn't we just write 6.06 comma 3.5? It's okay to think of this as just the x and y components of vector A. That's okay, but there's a little more to it that I want you to know. So, these symbols here, I hat and j hat, they're known as unit vectors. And all a unit vector is it's a vector whose length is 1. So this I hat is just a vector in the x direction whose length is 1. And j hat is just a vector in the y direction whose length is 1. That's all this means. And now here's why it's significant. With these new concepts, let's dive into this whole equation here and see what it's telling us. Let's build this equation using these concepts. We'll start with I hat, where that's just this vector of length 1 in the x direction. But watch what happens when I multiply it by this scalar of 6.06. We know how scalar vector multiplication goes, so I know that if I do that 6.06 times this vector of length 1 right here, it's going to lengthen it just like that. So this is 6.06 times I right here. Let's imagine our j hat, that's just vector of length 1 in the y direction, and let's multiply this vector by a scalar of 3.5. Well, that's going to lengthen this by a factor of 3.5. And now let's say I want to take these two vectors that I've assembled and add them up. Well, we know to add vectors, you do the tip to tail, you do that parallelogram method. I'll start by drawing my 6.06 I hat right here, draw it, finish at this point right here, and from that point I'll continue with my 3.5 j hat, and the sum, the resultant, the complete vector, is drawn from the very beginning here to the very end. And that is my vector A. So I wanted to build up this equation here using the concepts of the unit vector and the scalar times vector concept. All in all, it's okay to think of this as, alright, vector A has a x-coordinate of 6.06 and a y-coordinate of 3.5. I don't think that'll give you too much trouble, but you do want to understand the underlying mechanics here with unit vectors and scalar times vector multiplication and how they come together with vector addition to sort of build this vector A. So that's why these guys are here and why this plus is here. I mean, otherwise, when we wrote a vector, it could just be 6.063.5. But we got that unit vector concept and scalar times vector concept going on. And especially unit vectors are very, very important when it comes to certain engineering classes like dynamics and physics, things with motion. So check the practice video if you want a couple of practice examples doing scalar times vector multiplication, as well as with unit vectors. But other than that, that's it for this video.